This video is going to cover how to design beams and shafts. Effectively, beams and shafts, mostly the same thing. Shafts just kind of like skinny beams, probably more circular, whereas beams more rectangular members. But designs of beams and shafts is mainly two things. You have to check for the internal moment and the internal shear and know that it doesn't actually exceed the capacity of the member. And when we talk capacity, we're talking stress capacity. For bending, which is normal stress, and shear, which is shear stress. So again, we had two equations for that. For our bending, we had m times c divided by I. And for our shear stress, we have VQ over IT, our transverse shear. So effectively, we have to check for both of them. Now for long span beams, usually moment controls. Usually, but we always still have to check the other one. So we always need to check shear, just in case. For short beams, technically shear usually controls, but that's not as pretty of an equation as our bending stress. So when you have rectangular beams, it's not that bad because C is literally half the depth of a rectangle, right? So if you have a rectangle about the x-axis for causing bending, you have a moment, and C is obviously the half the height. I is just simply 1/12 base times height cubed, so it's really not that bad. If you're talking about like a circular shaft, again, it's really not that bad. For a circle, C is, again, same thing, half the height, and the moment right there. An eye of a circular shape doesn't actually matter either way. Same thing when you go to the transverse shear check. Doing this, Q is, of course, the area away from the neutral axis because the neutral axis is where the maximum shear occurs. And same thing for a circle. Not quite as lovely of an equation for the circle, but still it's really not that bad. And the little t over there, the thickness, is simply the total width of that shape. So either being the diameter of a circular shape or just the width of the rectangle. So again, really not that bad. However, when it comes to an I-beam, when it comes to an I shape, those don't become very fun anymore because again, you have to calculate moment of inertia of an I, and then Q for an I shape is half of this. And that means you have to calculate the centroid of the T and all sorts of other things. So that one's not very fun. But we have kind of a different thing that we're going to use for when we do I shapes, and that's the section modulus. And the section modulus is just capital S. And that guy is actually kind of a rework of this equation right over here. And he is just simply m over sigma. So as you can see, m is right here, sigma over here. So our section modulus is actually just I over C, because obviously you have to cross multiply there. So I over C is actually the section modulus, and that's going to be in terms of inches cubed. Well, what does this do for us? Well, what we can do is actually go into our steel tables, which is Appendix B of the Hibbler textbook that we're using, and you can go pull up section moduluses, and you can actually just go verify that as long as the section modulus that you pick is greater than the one that you calculated, congratulations, your beam's good for shear or for normal stress. Then you have to check shear. And shear is not very fun because, again, as you're imagining, this equation kind of sucks really bad. However, you may recall that technically for an I shape, we can get away with V over A, but it's area of the web specifically. So technically, it's going to be your shear over the thickness of the web times the depth. And again, where are you going to get this information? This information comes straight from the steel tables, which are Appendix B. So steel's actually really not that bad, though I guess it's a little bit worse compared to just rectangular beams and circular shafts. Primarily what you need to start off by doing is actually finding what V is and what M is, and how to do that is, again, just drawing a shear moment diagram and calculating the maximum if it's just not already given. So it's really not that bad. So let's pop to an example. So in this example, we have a very beautiful uniform distributed load, but only over half the beam. So it's kind of nice, but kind of also not nice. We have some ridiculous values for shear stress and normal stress that we're allowed to hit. And what we want to do in this case is find the maximum magnitude of that distributed load that we can put on it. Now I will say that I'm going to do this example forwards and backwards. So in this case, I'm going to find the maximum weight that you can put on it, but then in another minute, we're going to calculate it backwards. We're going to say, given a maximum W value, we're going to then go and calculate what size of beam we should use. So for this member, technically, it's actually a W8 by 31. So a W8 by 31 does have some certain properties, and we'll go pull up that appendix in a little bit. But again, first things first, we have to check for shear and moment, right? So technically when you design this member, we checked for shear and moment. So what is shear and moment? Because that's definitely going to give us how to calculate W. Well, we have sigma allow is equal to 300 KSI. And what we know about that is that's equal to M times C over I. But we really don't want to calculate any of that stuff. That's not really fun. So how about instead, we're going to look at it from the other perspective. Because we have a W shape, we can actually use S. So S is equal to our M, the moment, the maximum moment here, hopefully, but just our moment value divided by sigma allow. Okay, so what is S? That would be a great idea. So again, we're going to go look at the chart for W8 by 31. So here we have the charts. We're actually going to be looking at the x-axis when we do this, because usually you load your member across the major strong axis here to make sure that we don't have really terrible bending. So we're going to be primarily looking into this column right here. And again, we're looking for a W8 by 31 who's right here, so read across, and we find that our S value is 27.5. Okay, so going back, we said we had 27.5. This is in inches cubed, by the way, and that's equal to our moment divided by our 300 kips per square inch. It's definitely important to pay attention to your units here, because you're probably about to get something that you wouldn't normally think about. We're going to get a moment, but our moment's going to be in kip inches, which is awkward. We're actually going to get 8,250 kip inches, but who's ever going to talk about kip inches, especially when the length of your beam is in feet? So I should probably turn that into feet. So you divide by 12 and you get 687.5 kip feet. Yay, that's enjoyable. So cool, so we have our moment. However, what about shear? What about shear? Shear's a little bit easier, right? We have our shear equation, which we said was V over A of the web, right? Area of the web. So we have a value for our shear here. We said the allowable was 100 KSI, and that's going to be equal to whatever V is that we're trying to find over, again, we said that's going to be the thickness of the web times D. So back over here, we're looking for some new things here. We have thickness of the web, and we have the depth. So we're going to multiply 0.825, or 0.285, excuse me, 0.2825 times 8. So plugging that in, we're going to have 0.285 inches times 8 inches. So yeah, so we're going to get a value for our shear, and that's going to be 228 kips. Cool, because we have kips per square inch on one side and square inches on the other. So cool. So now that we have this, what are we supposed to do? Well, if you are looking at this wonderful picture, you realize that you could actually solve for at least a little bit of statics here. And we could have found things like what's AY and what's BY, and you might be thinking this isn't really helping me much. But again, if we draw a shear moment diagram, that's going to tell us what the maximum values are. So let's do that. So if we actually solve for AY and BY, let's go ahead and redraw this down here. We are going to have AY, and we're going to have BY. And again, it's 8 feet and 8 feet. And our distributed load here only goes from the middle over. And we said that was W. So if we sum the moments about B and set it equal to 0, we're going to be able to solve for AY. And AY here, let's just calculate it all out, why don't we? We have AY going around this way, which is negative. Cool, so we have negative AY times a grand total of 8 plus 8, which is 16 feet. BY is not going to create a moment, and then we do have W. W is going to be going this way, which is positive, woohoo, so we have plus W, and W acts across a total of 8 feet. But again, watching our units here, we have kips per foot, and we have feet, so now we're sitting at just kips. Kips is not a moment, so then we have to multiply by the distance of his centroid, which is right here, over to the point that we're looking at, which is 8 feet divided by 2. So cool, so what are we going to get for AY? We're going to get that AY is equal to 2W. Yeah, it's in terms of W, which really isn't that bad, but it's 2W kips technically going up. So we're just going to put 2W over here. Now, a very simple summation of the forces in the y direction, setting it equal to 0, and you're going to get, obviously you already had 2W's going up. You have a grand total of minus W going down, but that's W kips per foot across a grand total of 8 feet. And then we also have plus BY over here. So you have 8W minus 2W, so therefore BY is 6W, again in terms of kips going up. So 6W. Next, what we're going to do is actually create the shear moment diagram. So remember, at every load or every change in load, we're going to draw a line. And then we have our horizontal for shear. Positive and negative, again, this is in kips. And then again, we have the same thing, but for moment over here. Cool, and the moment again is in kip feet because it wouldn't make sense to have it in kip inches right now. So remembering how these lovely things work, you start at 0, you end at 0. You start at 0, you end at 0. So easiest thing to do with our shear moment diagrams right now. And for shear, if it goes up, the arrow goes up, you go up. So it goes up by 2W. So here I am at 2W. Then nothing happens, nothing happens, nothing happens until this point. So nothing happening is a 0-degree slope, the distance being 8 feet. At this point, we start to go down, right? But it's a kind of a linear thing here. So we go down to down to down. And at this point, how far down are we going? We're going down a total of W times 8. So 2W minus 8W, oh my gosh, magic, we're down at 6W. And then we need to go up by 6W, and who would have guessed it, we're back at 0. So again, this is a 1-degree slope, but what is this guy? What is X? How do you find that again? Well, we're gonna do some similar triangles. So we have a grand total of 2W over X distance. That's the small triangle here. And then we're gonna relate him to a really big triangle, and that big triangle is this guy. Yeah, big dude there. And that is what? That's a height of 2W plus 6W for a grand total of 8W over the whole 8 feet. So wow, that doesn't take much to tell that x is actually equal to 2. 2 feet there. So if this guy is 2 feet and this guy then is 8 minus 2, which is 6 feet. What's our maximum V though? If I'm looking at this, V max is going to be 6W, right? That's kind of important. So we should write that off to the side somewhere over here. So V max is 6W. It doesn't really matter if it's positive or negative. The point is it can only handle a certain amount of stress, and that stress is going to be from the maximum shear. So that's 6W. Now for the moment diagram, which again is really not that bad. We start and we end at 0. And we have a 0 degree slope, so this one's going to turn into a single degree, so 1 degree slope. What is the area under the curve? 2W times 8, that's 16W. And then we have a 1 degree slope. It's still positive, so we're going to be going up to about right here, maybe-ish, about right there. And so the area of that triangle is 1/2 the base of 2. Great. Times the height, which is 2W, so that area is 2W, so 2W plus 16W, 18W. And then we take a turn to go down, and then we have minus 1/2 the base of 6 times the height of 6. And wow, lo and behold, it is 3 times 6W, which is 18W. So we do end up back at 0. So again, what's our maximum here? 18W. So M max is 18W. Now what do I do with this information? Well, you may recall from just a little bit ago, we actually had a maximum moment and a maximum shear. So we literally just set those equal to each other, right? We said V max was, I literally just forgot it, 228 kips. Yeah, we said 228 kips. Wow, so 6W is equal to 228. So lo and behold, you get a value for W, and that value for W is 38. Isn't that impressive? Kips per foot. And then our moment, we're going to set that equal to whatever our moment was. Our moment was 687.5. 87.5. Again, this is in kip feet. All right, and then we're going to get that W then is going to be, and again, kips per foot, and that's going to be 38.2 kips per foot. So when we want to know what the maximum is, if you put 38.2 on this thing, that's going to exceed the maximum shear and break the beam. So actually our maximum is not just the biggest number. Our maximum is the smaller number. Right? With design, usually it is the smaller number. So that's the maximum value for the distributed load that we could actually stick on this member. Okay, so that's one way of doing that. That's analysis, though. That's not design, and we're supposed to be talking about design. So instead, let's do it. Same thing, slightly different. So this time, more realistic numbers perhaps for our actual shear stresses and our normal stresses, at least for our allowable ones. We still have the same 16-foot beam, still the distributed load only goes over half of it. This time though, we're going to say that the W value is 5 kips per linear foot. And what we want to do is find the lightest W shape. So a little interesting thing about W shapes before we get started. Obviously, they're called wide flange, and wide flange does mean it's an eye. That was a very ugly eye, but still nonetheless, it's an eye shape. So when we say I-beams, these are actually what we're talking about, and they're called wide flange, hence the W. So how they're read, if you haven't noticed, is a W with a number, X, and another number. So we would say W blah by blah. So before we had a W8 by 31. So what do these numbers even mean? Well, this number right here is the depth. That's the depth, approximate depth. Usually it's somewhere in that ballpark. So that's the depth of the member, depth of course being this much. It's not a perfect number. Again, you need to go look back at the charts, but again, you'll notice that they're all roughly around that area. And then this number over here on the other side, this is the weight. So technically all members do have a self-weight, right? You don't have something made out of a material and just have it not weigh anything. So this is the weight in pounds per linear foot. So technically it already has a distributed load already on it, right? Because it exists. But we're just going to kind of ignore that right now for what we're doing in this class. So when we're looking for the lightest W shape, we're looking for the smallest number on the after the X part. So what do? Well, kind of the same thing, but in reverse. So what we're going to do is calculate, again, we have to start with moment. So to do moment, we're going to calculate S, right? It's moment over sigma. So we're going to start by designing for moment. Well, in order to do that, I kind of need to know what my moment is, and thank God I literally just calculated those things over here, right? We literally said with that exact same setup, the maximum moment was 18W, and the maximum shear is 6W. And I have a value for W. So what I'm going to do now is actually plug in my values for Vmax. Again, we said 6W, so 6 times 5 is 30 kips. And then we had Mmax, and we said Mmax is equal to 18W, so 18 times 5. Not necessarily something you know off the top of your head, but that is 90 kip feet. So I want to come over here and I want to plug in 90 kip feet. Okay, but then divided by sigma. Sigma we just said is over here given 50 KSI. I have a little crisis with my units over here. I have feet and I have square inches. So I need to convert it to something that's going to be read in the table. And you might recall that S was actually in inches cubed. So we need to convert this guy out of feet and into inches. So ta-da. So now I'm going to calculate S, and S is going to be equal to 21.6 inches cubed. So what do I do with this information? Again, we're going to go to the steel tables, and again, that's Appendix B. So in Appendix B, that is what's right over here, right? In Appendix B, they're going to show you again, this is what an eye looks like. Notice that there's some itty bitty little curvature here, which does make that practically impossible for you to be able to calculate the moment of inertia correctly. Same thing with the section modulus, because technically it's the moment of inertia in that calculation as well. So because of that, we have all these wonderful tables. So we're looking for the lightest W shape. So again, we're looking on our picture over here, we're looking for the smallest number over here, but we also do have to be looking in the S column and making sure that our S value is greater than 21.6. So I'm going to go for each one of these, right? Let's start with what would be our W6. W6 by what? Which one of these S values here is greater than 21.6? None of them? Okay, so just kidding, not a W6. How about a W8? So on the W8, we're in this bracket now, and we're looking for something that's greater than 21.6, and the first one we find is, yet again, our W8 by 31. Okay, let's go up to our next bracket. We have a W10 by, now what? Now we're looking in this area. The first one that's greater than 21.6 is this guy, who is a W10 by 30. Okay, 30 slightly lighter than 31, just saying. And then we have a W12 by, looking now into this area, W12 by, 25.4, just ever so slightly above 21.6. And that's W12 by 22. Nice. That's great. What about the other side? Well, there's technically the W14s, So W14 by, and again, we're looking for SX here across the strong axis because it'd be kind of stupid otherwise. And we find 29, which is a W14 by 22. This is not exactly any lighter. Then we have the 16 by, and our lowest one here is greater than 21.6, 16 by 26. Okay, now we're going in the wrong direction. The lightest W18 would be 35, so how about no? And the lightest 24 is 55, so how about no? Again, we could have said the same thing here. 26 is not lighter than 22. When we have our choice between a 14 by 22 and a 12 by 22, most likely we're going to go with this guy. However, we can't just say that that's the answer. No, we actually have to check, again, our shear. So we need to check that. That's going to be V over area of the web. So what was V? That's a dang good question. Let's go find it. We said 30 kips. 30 kips. And also our allowable shear stress is 10 KSI. So we said 10 KSI for our shear stress is what we're going for here. We have to be less than that value. And we said 30 kips divided by what's a W. So again, that was D times TW, our two things in red here. And we are looking for our W12 by 22, so we're here. So we're going to multiply 0.260 inches by our 12.31. And what do we get? Lo and behold, we're actually going to get for this guy 9.37 kips per square inch, which is in fact less than 10. Go us. So when they ask us for what is the lightest W shape, our answer is going to be a W12 by 22. So that's pretty much it on designing beams and shafts.